chair or, the sofa you were sitting on right now, or maybe the car seat you were driving in.
Yeah, we just take it for granted, right?
Exactly. You probably look at it and just see a single piece of furniture, like a cohesive, finished object. But if you strip away the outer layer and look at it from a manufacturing standpoint, that seat is an incredibly complex 3D jigsaw puzzle.
Oh, absolutely.
It is a dense, highly engineered layering of fabric, leather, vinyl, flexible foam, heavy cardboard, and rigid structural components.
It really is an engineering marvel when you break down the physics of it. I mean, you have all these disparate materials interacting. Some are highly flexible and stretch on a bias, some are completely rigid, and they all require entirely different handling and processing techniques.
Right.
Yet they all have to come together seamlessly to create a final product that is comfortable, aesthetically pleasing, and, durable enough to sit on every single day.
And the source we are diving into today pulls back the curtain on exactly how that happens in the modern era. We are looking at technical documentation and a comprehensive deep dive from velocity plotters and cutters. It's titled Automation for Furniture and Upholstery: Real Benefits.
A really fascinating read.
It really is. The mission for today's deep dive is to take you step by step through the highly technical world of upholstery automation. We are going to explore the what, the why, and the exact mechanical and software solutions that turn a historically chaotic manual craft into a streamlined digital powerhouse.
Yeah, that transition is wild.
Okay, let's unpack this, because when we say automation in this context, it's so easy to picture a sci-fi scenario with robot arms completely replacing a workshop of artisans.
Right, and setting the baseline here is critical because that is a massive misconception.
Yeah.
Automation in furniture and upholstery manufacturing is not about stripping the human out of the loop or entirely replacing workers. It is fundamentally about using sophisticated software and specialized machinery to eliminate time-consuming, highly variable manual tasks. The core goal of this technology is reducing the massive tolerance gap between what a furniture designer originally intended on their screen and what actually gets produced on the factory floor.
So, to understand the solution, we first need to understand the mechanics of the problem. Why is manufacturing a sofa or a car seat so incredibly difficult to standardize? I mean, if we can mass produce plastic cups with zero variation, why is upholstery such a bottleneck?
Well, it comes down to the inherent variability and physical degradation in manual processes. Think about a traditional upholstery workshop.
Okay, I'm picturing it.
For decades, the standard practice has been to create physical templates for every single piece of a furniture design. These templates are usually cut out of heavy paper, dense cardboard, or thin sheets of wood.
Right.
An operator takes that physical template, places it on a roll of fabric, manually traces the outline with chalk or a marker, and then cuts it out with heavy shears or a manual rotary cutter.
Which, I mean, that sounds completely fine if you are building a custom one-off chair for a single client.
Yeah, for a one-off, sure. But it is disastrous for consistency at scale. Every single time you run a piece of hard chalk around the edge of a cardboard template, the friction wears that cardboard down slightly.
Oh, wow. Of course.
The edges fray and soften. If the workshop is humid, wooden templates will warp. Over hundreds of tracing cycles, the physical template itself actually changes shape.
Just from normal use.
Exactly. And that is before you even factor in the human mechanics, like the angle at which the operator holds the chalk, the thickness of the chalk line itself, or, how much tension they apply to the fabric while holding it down to cut.
So you get this compounding tolerance stack up, a millimeter lost on the cardboard, another millimeter added by a thick chalk line, and suddenly the piece is completely out of spec.
That is the exact problem. A tiny variation of just a few millimeters in drawing a pattern, placing materials, or cutting translates into massive assembly problems down the line. The fabric won't stretch correctly over the foam core, seams will pucker, and you basically end up with wasted material and heavy rework.
So the first logical engineering step is getting rid of the degrading cardboard entirely. How do we actually get from a physical workshop with stacks of dusty, warping templates to a pristine digital file?
That requires high-fidelity digitizing. The source specifically highlights a technology called the V-Shoot camera digitizing system. Now, it's important to understand this isn't just snapping a JPEG with a smartphone.
Right, because a phone camera distorts things, right?
Exactly. Standard camera lenses introduce optical distortion. They curve straight lines at the edges of the frame, which is called barrel distortion. The V-Shoot is a high-precision calibration system. The software mathematically corrects that optical distortion to achieve sub-millimeter accuracy.
Sub-millimeter?
Yeah, it's incredibly precise. It captures existing physical patterns, which, by the way, often represent years of a master craftsman's trial and error experience in getting the fit just right. And it instantly converts their exact geometry into a vector-based digital library.
So it's essentially acting as version control, like a GitHub repository for physical objects.
I love that analogy, yeah.
Instead of relying on a physical cardboard cutout that degrades over time, like playing a game of telephone where the shape gets slightly more distorted every single time it's copied, you digitize it once to perfectly preserve that craftsman's technical knowledge forever.
That is a perfect way to look at it. You are immortalizing the geometry.
But once you have that perfect digital snapshot, how is it actually manipulated? Even a distortion-free image file doesn't tell a cutting machine what to do.
Right, and that is where the computer-aided design, or CAD, step becomes the central nervous system of the operation. The digital vector file is imported into specialized parametric software, like Velocity's Vectograph CAD.
Yeah.
And this isn't a basic drawing tool like Microsoft Paint. This software allows manufacturers to digitally define every single structural and behavioral attribute of the pattern. You aren't just defining the outer contours.
What else are you defining?
You are calculating precise seam allowances, defining structural perforations, plotting internal reference lines for where a zipper will go, and adding alignment notches.
Oh, I see. So it takes a flat 2D shape and adds the manufacturing metadata. It calculates exactly how much extra fabric is needed to fold under a wooden frame to receive a staple, or how a 2D piece of leather needs to curve to wrap around a 3D foam armrest.
Exactly. And because that metadata is entirely digital, it never warps, it never shrinks, and it never gets lost in a dusty pile in the back of the workshop.
Okay, so we have our patterns perfectly digitized. They are pristine data-heavy files on a server. But now we move from the design phase to the preparation phase. We have to actually put these digital shapes onto physical material. High-end upholstery fabric, and especially leather, is incredibly
Oh,
expensive.
massively expensive.
Right. So if a human isn't manually placing these templates to save space, how does the software make sure we aren't wasting a fortune in offcuts?
Well, that brings us to the mathematical science of digital nesting. Nesting is essentially an advanced algorithmic puzzle, functioning highly similarly to Tetris, but with complex, irregular polygons.
Sounds complicated.
It is. The software takes all those digitally defined parts, the seat cushion, the armrests, the back panels, and automatically arranges them within the specific width and length parameters of a digital roll of fabric.
And it calculates this faster than a human could visually estimate it.
Significantly faster. The algorithm computes thousands of different combinations a second. It rotates, flips, and interleaves the patterns, computing the absolute tightest geometric density possible. It leaves the microscopic minimum amount of unused space between parts, ensuring you get the maximum yield out of every single yard of material.
Wait, I get how that works flawlessly for a uniform roll of synthetic fabric where every single square inch is identical. But what about leather? Leather is an organic animal hide. It has natural defects, bug bites, scars, variations in thickness, and very specific grain textures.
You know, leather's tricky.
Right. A computer prioritizing pure mathematical density is going to put a giant cow scar right in the middle of a luxury chair cushion if it isn't careful.
Well, what's fascinating here is that the source addresses this exact biological variable, and it is an incredible engineering solution. The software does not operate blindly. It uses a human-in-the-loop hybrid approach. It combines the raw computational power of the digital optimization algorithm with the nuanced visual criteria of a human operator.
Oh, okay. So the craftsman is still heavily involved in the material prep.
Absolutely. The human operator inspects the physical hide, they identify the surface quality, note the direction of the grain, and digitally map out any defects or scars onto the system. The nesting algorithm then runs its density calculations around those human-defined constraints. It ensures that the premium, flawless zones of the hide are mapped for the highly visible seat cushions, while the areas with minor imperfections are automatically nested for, like, hidden structural panels underneath the sofa.
That is brilliant. It respects the organic nature of the material while still applying ruthless mathematical efficiency to the layout. The benefit there is massive. better use of expensive materials directly leads to significantly lower operating costs.
Huge cost savings.
Plus, it creates a far more sustainable, resource-efficient manufacturing process because you are drastically reducing scrap and rejected pieces before a single cut is even made.
And, sustainability in this industry isn't just about sourcing eco-friendly textiles.
Mm-hmm.
Fundamentally, it is about maximizing the yield of whatever resource you are pulling from the supply chain. Algorithmic nesting achieves that effortlessly.
Okay, so we have our highly optimized, digitally nested layout mapped out. Now we have to physically cut it. And this is where the market demands get incredibly tricky because we are moving away from the era of mass producing thousands of identical items. Every modern customer expects a bespoke, customized piece.
Yeah, everyone wants something unique now.
Exactly. They want a slightly wider seat, a denser foam core, or a very specific modular configuration. Manually, accommodating those custom dimensional requests is a logistical nightmare.
It is a total efficiency killer in a manual workflow. If a customer wants a standard sofa design, but they want it just 2 inches deeper, a pattern maker has to draft entirely new cardboard templates from scratch for the seat, the sides, the base, and the foam.
Just for 2 inches.
Just for 2 inches. That takes days of drafting preparation before a single piece of fabric is cut.
But with parametric CAD software,
Those modifications are applied instantly to the production files. You open the Vitagraph CAD file, adjust the dimension parameters to add 2 inches to the depth, and the software automatically recalculates all the intersecting seam allowances and renests the new layout in seconds.
which brings us to the hardware that actually turns that custom file into a physical object. How does a manufacturer physically cut this dynamically changing layout?
The documentation introduces the Velocity ProCut X single-ply cutter as the solution for this agile scenario. This is a massive piece of digital cutting hardware built around a conveyor-style work table.
Like a treadmill.
Sort of, yeah. That conveyor means it can pull and process continuous lengths of materials straight from the roll. But the real engineering feat is the tool head. It doesn't just drag a knife through the material.
Because dragging a standard blade through something soft like polyurethane foam would just snag and tear it. Right?
Precisely. It would destroy the edges. So the cutting head uses oscillating blades. These blades move vertically up and down at incredibly high speeds, essentially microsawing through the material, while the gantry moves the head laterally across the table.
That makes a lot of sense.
Yeah, and it also features rotary knives for woven fabrics and punches for structural holes. It performs complex contours, drills holes, and makes notches all in one continuous motion, exactly mapping the digital file to reality.
Now, the documentation makes a big point about drawing a distinction between single-ply cutters and multi-ply cutters. Just looking at the physics of it, I imagine single-ply is incredibly agile, but probably too slow if a factory needs to fulfill a contract for, like, 5,000 identical hotel beds.
Yeah.
Is that where the different hardware comes in?
You've hit the nail on the head. It comes down to volume versus flexibility. Single-ply cutters, like the ProCut X, cut exactly one layer of material at a time. They are built specifically for flexibility, custom orders, prototypes, and low to medium volumes, where the design changes from one order to the next.
So very adaptable.
Very. You can rapidly switch from cutting a velvet sofa design to a leather car seat design in 5 minutes, because there's zero physical setup required.
And multi-ply machines handle the hotel contracts.
Right. Multiply cutters are for massive, repetitive production. They use a vacuum system to compress dozens, sometimes up to 100 layers of fabric together into a rigid block.
Wow, 100 layers.
Yeah, it's intense. Then a massive, heavy-duty reciprocating blade cuts out 50 identical sofa cushions simultaneously. It is incredible for sheer output capacity, but it is entirely the wrong tool if you were trying to fulfill individual, customized orders.
Here's where it gets really interesting, though. The speed of the automated cutting machine is an obvious benefit, but the source highlights a massive downstream benefit that fundamentally changes the assembly process, drastically less rework.
Yes.
Because the digital cutter places physical notches, marks, and perforations exactly where they belong with millimeter precision, it acts as a perfect roadmap for the sewing personnel.
And this is perhaps the most profound shift on the factory floor. When parts are cut manually, operators often have to stretch or ease the fabric on the bias to make poorly cut asymmetric pieces fit together.
That sounds frustrating.
It is. That stretching distorts the corners, creates uneven tension, and leads to peckered seams.
They're basically guessing where the pieces should align and forcing the fabric to comply.
But when a digital cutter processes the fabric, it punches tiny alignment notches into the seam allowance, exactly where two complex curves must meet. The sewing operator doesn't have to guess, measure, or interpret anything.
They just line it up.
Right. They just align notch A to notch A and run it through the sewing machine. It guarantees that corners remain perfectly square, seams match flawlessly, and the upholstery skin fits over the foam core like a glove every single time. It completely eliminates the guesswork and the bottleneck at the sewing station.
We've talked extensively about flexible materials, the fabrics, vinyl, and foam. But furniture isn't just soft stuff. It requires a skeleton. Factories still rely heavily on physical production markers and need to process incredibly rigid materials for structural support. How does the hardware ecosystem adapt when the physics of the material totally change?
Well, it requires a diverse architecture of machines. A conveyor belt digital cutter is fantastic for textiles, but useless for a thick sheet of plastic. The source walks us through the specific hardware ecosystem required to run a full plant. First, you have to manage the physical paper trail. Factories use roll-fed industrial plotters.
Plotters?
Yeah, machines that draw vector files onto massive rolls of paper.
Wait, what are they plotting on paper if they already have digital cutters?
They are plotting markers. In manufacturing, a marker is a massive, full-scale printed map of the nested layout. These are critical for design development, pre-production validation, or for guiding operators who are still cutting certain specialized materials by hand.
Ah, okay.
Velocity provides machines like the Technica 1 for design validation and the heavier-duty Vector series for high-volume marker printing. They even offer hybrid machines that print the design and perforate the paper in one pass to create physical stencils.
But a roll-fed machine, by definition, requires the material to bend around a roller. What about the rigid structural stuff? You can't roll a thick piece of PVC or structural cardboard.
Which is exactly why the ecosystem includes flatbed plotter cutters. Instead of feeding material through rollers, a flatbed machine features a large, completely static vacuum table.
Like an air hockey table in reverse.
Kind of, yeah. The rigid sheet of heavy cardboard or plastic paneling lays perfectly flat and immobile, while the heavy-duty cutting gantry moves over it. It is essential for cutting the non-flexible structural components of the furniture, or for creating highly durable, rigid prototypes.
This all sounds like a perfectly synchronized orchestra of machinery. But here's an operational question. What if a workshop wants to buy one of these advanced digital cutters, but they've been using a totally different legacy CAD software for the last 15 years? Do these machines lock them out unless they buy the proprietary software too?
Yeah, data conversion is a notorious hurdle in industrial automation. Different software speaks different mathematical languages. But the documentation addresses this directly with a conversion tool called EasyPlot. It acts as a universal translator for vector math.
How does that actually work under the hood?
It takes standard design files, like DXF and DWG formats, which are industry-standard vector files used by dozens of different CAD programs to define geometry, and it translates them into machine-readable PLT or HPGL formats.
And what makes HPGL different from a CAD file?
Well, a CAD file defines the shape theoretically. HPGL is a hardware control language. It translates that shape into specific X and Y coordinates that tell the servo motors exactly where to move the physical cutting head.
Okay, that makes sense.
By providing that software translator, a manufacturer can upgrade their physical cutting hardware without suffering the massive disruption of completely abandoning their existing design software.
Which brings us to the final major piece of this puzzle: implementation, traceability, and support. We've gone through the whole production life cycle, but how does a business owner actually manage this massive influx of digital data once it's running?
It completely revolutionizes production control through digital traceability. In a manual workflow, archiving patterns is a nightmare of physical storage. In a digital workflow, every single cutting file is meticulously stored on the server and tagged by the customer's name, the material type, the exact date, and the version status.
That completely eliminates the administrative nightmare of physical archiving. If a customer buys a custom sectional sofa and 5 years later their dog ruins one specific cushion.
Yep, happens all the time.
You don't have to dig through a warehouse hoping the cardboard template hasn't rotted. The exact approved digital geometry of that specific customer's cushion is instantly retrieved. You send the 5-year-old file to the ProCut X, and it cuts a replacement piece with the exact millimeter precision of the original.
Exactly. There is zero degradation of information over time.
But hang on, this all sounds incredibly efficient on paper. In reality, you are taking a workforce of traditional craftsmen who have spent 30 years working intimately with a pair of shears, a piece of chalk, and a physical template, and you are putting them in front of a CAD screen and an algorithmic nesting program. How does a business actually survive that operational whiplash?
That is the most critical challenge of implementation. The documentation stresses that automation must be highly scalable. A business should not undergo operational whiplash by buying the biggest multiply cutter available on day one.
Right, that would be chaos.
You have to evaluate your daily volume, the frequency of customization, and your workforce's technical literacy. A traditional workshop might start strictly with the V-Shoot digitizer and the CAD software just to get their physical patterns preserved digitally, while they continue to outsource the actual cutting.
So they slowly build the digital muscle memory before overhauling the physical factory floor.
Precisely. Later, as order volume grows and operators get comfortable, they can integrate a single ply cutter.
But as we read through the source material, there was one point that stood out as the hidden secret to actual success in this industry. It wasn't about the precision of the oscillating blade or the processing speed of the nesting algorithm. It was entirely human.
Yes. If we connect this to the bigger picture, the absolute best technical specifications in software math in the world mean absolutely nothing without robust after-sales service. When a factory automates, a digital cutter becomes the central beating heart of the production line. Everything flows through it.
So if it breaks,
If that machine goes down, your entire factory stops.
you can't just hand everyone a pair of scissors and tell them to catch up to an algorithm.
You would be paralyzed.
Yeah.
So a manufacturer must heavily evaluate the human service infrastructure before buying the hardware. What are the technical assistance response times? Do they have a robust spare parts inventory located domestically so you aren't waiting on international shipping?
Yeah.
Are replacement oscillating blades easily available? Do they offer comprehensive on-site operator training?
Yeah.
Protecting the investment from extended downtime through human support is just as critical as the speed of the machine itself.
We have covered an incredible amount of ground today. Let's recap the journey. We started with the physical bottleneck of traditional manufacturing, tracing degrading cardboard templates and the compounding errors of manual chalk lines. We solved that by mathematically correcting optical distortion and digitizing those templates with the V-Shoot camera system.
Yep.
We then took those pristine vector files into Vetagraph CAD, where we added critical manufacturing metadata like seam allowances and notches. We moved to material preparation, using algorithmic nesting to calculate thousands of combinations a second, squeezing every usable inch out of expensive fabric while a human operator mapped around the natural defects of leather.
Exactly.
Finally, we sent that optimized layout to a machine like the ProCut X, which microsaws through the material with absolute precision, providing a flawless physical roadmap for the sewing teams downstream. It is clear that automation here isn't just about raw machine speed. It is about a digitally connected workflow that eliminates compounding variations, removes repetitive physical tasks, and turns a historically chaotic craft into a precise, repeatable science. So what does this all mean?
Well, I think it leads to a fascinating philosophical shift in how we evaluate and value manufacturing. We often naturally romanticize the idea of handmade furniture. We associate manual processes with high quality, bespoke luxury, and, the soul of true craftsmanship.
For sure.
But if automation, through distortion-free camera digitizing and precision digital cutting, actually preserves a master craftsman's exact geometry flawlessly forever and completely prevents the inevitable human errors of manual tracing, stretching, and cutting it, raises an important question.
Does true quality in the modern era actually rely more on sophisticated software perfectly preserving a master's intent than on a human hand holding a pair of scissors?
Exactly. Does the perfection of the code actually honor the craftsman more than the charm of the manual flaw?
That is a brilliant thought to end on. Something for you to ponder the next time you sit down on your perfectly upholstered sofa and look at the seams. Thank you for joining us on this deep dive into the hidden world of manufacturing geometry. Hopefully, you'll look at the furniture in your own home or the seat in your car just a little differently today. We'll catch you on the next one.